Hello, it's David at DSES UK, and today in this whiffle-filled presentation I'm talking test rigs. Something that'll be of interest to those who are wrapping their noggins around inspection and testing and who want a controlled environment where they can run through the common features of a multifunction test instrument without fear of plunging their other half into darkness partway through them gulping over yet another tattooed nightmare on naked attraction. Some viewers may be aware of my own test rig setup, which has been bolted onto my wall of interesting tat in one form or another through many a video I've spouted out since 2018. But here I'm going to show you how to shrink the essence of all this bollocks into a smaller and relatively more portable format. After all, not everyone has a handy wall upon which they can slap a contraption such as this little lot. This video will provide a part listing and detailed deconstruction of an RCD protected 3-circuit test environment consisting of a ring socket circuit, a radial socket circuit with USB outlet, and a 3-way lighting circuit, followed by a run through of testing to BS 7671 18th edition Amendment 2. This was requested by Sammi and Ria in Aberdeen, so if you find such content to be boring, and I must admit this one will be drier than a nun's smudger, then it's all their fault, not mine. And in true Blue Peter fashion, here's one I made earlier. It clocks in at about 8.5 kilos with dimensions approximately 620 by 440 millimeters by 250 millimeters deep, making it small enough and light enough that it can be considered transportable. It plugs into any socket outlet, regardless of whether that outlet is RCD protected or not, and it will allow one to perform a wide array of tests without tripping out any devices upstream in the home consumer unit. Assuming I haven't ballsed up the construction, that is. On the dead test front, we'll be able to perform ring end-to-end resistances, R1 plus R2, R1 plus RN, R2, well, you get the idea. Any combination of resistance tests you happen to have a hard-on for. We can also perform IR testing at whatever test voltage we fancy, and thanks to the design, we can play with IR both with and without loads being present. There's also an inherent IR fault built into this son of a bitch, which we'll see in action later. On the live test front, we have ZS-DB, which we can consider as our external impedance, or ZE, as well as final circuit ZS, RCD disconnection times, and even some clamp meter current testing. By design, the construction of this mechanical asshole also allows us to see the effect of capacitance in our wiring, something common on unearthed switch drops, which will affect certain LED lamps. When we come to the testing, I'll apply the mathematics as we go along to show what should appear on the tester's screen and why. As it happens, we'll also get to see RCD uplift in action. And if you don't know what that is, you will later. If you want to take things a stage further and install an AFDD, or indeed modify this in any other way with additional circuits, LED dimming, smart technology, or whatever, then of course you can do so. The whole idea of a test rig is for it to be at your disposal to experiment on, albeit safely, that is. I should perhaps shoehorn a disclaimer up the bum of this video at this point and state that the only people attempting to construct and to piss around with such a contraption ought to be those who are already well versed in electrical installation and the safe working around live equipment. The idea of this thing is for those who already know their onions and who are levelling up into inspection and testing to have an environment that's under their control where they can put in some practice. Of course, I can't speak for the competencies of anyone out there who may happen to be watching. I only know my own skills and limitations, and I only know that I can personally both build and use this cobblers without disastrous results. If anyone happens to mimic what I do here today and they subsequently come to a sticky end for failing to operate in a safe manner, then that's their fucking lookout. Your responsibility and safety, dear viewer, is your own. So if you're going to go twiddle the screwdrivers for yourself, be sure you're already well versed with electrical work, safe isolation and the likes of GS38. There's some helpful blarney and links in the description. So use this information at your own risk, but even if you don't go ahead and build the damn thing, I can still show you what I've done, how it works, what test data we can get out of it, and how the numbers hold up against what's presented in BS 7671. There will be one or two surprises along the way, either by design or not. So stop twiddling with your undercarriage, you pervert, pull your hand out of your pocket, and let's talk turkey on test rigs. First though, I'm going to have to dismantle this goddamn thing, just so as I can put it back together again for you today. Truth be told, I've already filmed construction twice. Once with Nick Bundy over in his unit in Stafford at the beginning of October, then again with Nigel back in the Twat Cave in early December. But in both cases, something didn't gel quite right and it all took too long. So I'm going to go through it again on my own today, which means I can chop and edit this together more concisely, so that if you've got YouTube running on autoplay, it'll click over to something more interesting for you sooner. Okay, so I won't disassemble it completely. You don't need to see me screwing shit to a backboard, so let's briefly talk about the basic bits that at least get us going. And speaking of backboard, well, first you're going to need one. That can be a slab of MDF, chipboard, Conti board, or whatever. In terms of sizing, mine is 620 by 440mm, and as you saw by the footprint of the odds and sods laid out upon it, there's not a lot of space left over, so it'd be harder to get it much smaller. That asshole Nick Bundy kindly gave me this bit of MDF I'm using here when I visited his unit, and that's the only component part, aside from one other, that I don't have a ready stock code for. Talking of which, I scouted around at the end of last summer for a one-stop shop who would be able to provide as many of the parts as possible, and in the end it was clear that City Electrical Factors were the only outfit with a UK-wide reach and ready availability of all but 2 items, one of which being the aforementioned backboard. For everything else, I'll give you a CEF stock code and the CEF list price that's correct at the time of recording. You may visit dscs.uk/testrig for that. No doubt you may be able to shop around if you're prepared to do so in order to save yourself some pennies here and there. I did consider trying to get into bed with a retailer so that you could just rock up with a single stock code for simplicity and perhaps also get a Bundy 10 style discount. But I doubt there'll be much take up on this, and most suppliers, including CEF, would likely just tell me to fuck right off had I asked them to do me a favour. One last thing, and I know you're impatient for me to get to the bloody point and to get started, but I want to state that I've aimed for simplicity of construction here. This is not the one and only way to bolt this kind of contraption together, but it is a procedure that aims to use as few parts as possible to save on both effort and expense. This is not how you would install such equipment out in the real world. As an example, I've deliberately avoided the use of conduit to link accessories together. The reason for this is that you would need to buy a 2 or 3 metre length of conduit and go to the effort of cutting it to size, which, for a rig this small, seems like overkill, as but a few centimetres of the stuff would ultimately be needed. If you want to buy conduit and use it, albeit with a load left over, you go right ahead, mate. But I've employed 3 other means for connecting the accessories here which, while not so much real world, are at least adequate for the task of slapping together a test rig. The first connection method that I've employed between the CU and the accessories here on the socket circuits is the classic 20mm galvanised coupler with a brass bush at each end. This looks a bit weird when used with plastic accessories, and I don't know why there isn't a plastic version of such a thing, but it's perfectly fine for the task of joining one accessory to another here in bullshit test environment make-believe land. Of course, you could plump for metal clad rather than plastic accessories if this kind of fuckery fucks with your fucking feng shui a little too fucking much, but your aesthetics are your own. The second option, used here between the socket accessories, is to couple a standard female conduit adapter with a 20mm bell mouth bush, which all sounds rather wonderfully lesbionic, and if that's not a real word to wrap your tongue around, then it ballywell ought to be. Okay, so this arrangement looks a little clumsy. Nonetheless, they do hold fast and join in a secure way which satisfies our test environment. The third option is to use a 20mm nylon compression gland, which looks on the CEF website to be exactly like the plastic coupler we wished for in our wet dreams earlier, but in actuality one end is just 16mm and won't quite fit a 20mm cutout. You'll also need to buy in 20mm lock nuts to go with the thing. Nonetheless, up to 6 2.5mm wires can just about be squeezed through if the rubber Johnny insert is removed, so for this application where I've used it between light switches, it will just about do the business. I'm employing all 3 of these methods here, but you go with whatever floats your personal boat. Again, you can do it the proper way with custom cut conduit if you prefer. My point here is simply to offer 3 alternatives that will serve for a basic test rig without you having to buy 2 or 3 meters of plastic tube you may not want. The basics have been secured to the backboard with 3.5 by 12mm self-tapping screws. The consumer unit I'm using is a British General garage board, but you can use whatever you want. CEF do sell a Luden board, which is perhaps better suited and is cheaper, but although it's a three-way enclosure, they seem to provide only a two-way buzz bar, which is pretty fucking ridiculous. I honestly don't know what goes through the manufacturer's heads sometimes. Most of them seem to possess the common sense of a clagnut. My own test rig is made up of bastardised parts from an insulated Crabtree Starbreaker CU, an MK main switch, Schneider protective devices, a Siemens AFDD. It doesn't matter, it's a test rig, it's not a real world install. You can use something from straight off the scrap pile if you have it to hand. This BG board comes with both a 6 amp and a 32 amp MCB supplied as standard, along with an RCD which, rather inexplicably for late 2022, is Type AC rather than Type A. Yeah, watch out for that. Still plenty of them in the supply chain, it seems. I've added a third MCB to it, that being a B16, because I'll be running 3 final circuits with ring sockets, a radial socket and lighting. The 29mm Patras accessories are Click Skolmore conduit Patrases, as these have a 20mm knockout top and bottom, unlike other brands which tend to have them on just one side. The 3 accessories closest to the consumer unit are deeper 47mm conduit Patrases, simply because the BG board's knockouts are offset from the backboard by more than a 29mm Patras can accommodate. I don't know what BG were expecting you to connect to their gear here, so you'll need to mark out and cut an appropriate aperture into a deeper Patras using a 20mm hole saw, hopefully not quite as off-centre as some of mine are. You could use something like flex conduit to get around the height differential between the CU and the accessories, but again that's introducing complexity I'm trying to omit from this build. Conduit Patrases are a more flexible plastic than standard Patrases and are easy to drill with a decent Armeg hole saw. The lighting circuit of the test rig uses this angle box which comes off the shelf at CEF and allows the BG board to mate directly with a 47mm Patras. I've gone for this for simplicity as it's a single component part to order in. A standard white right angle conduit box could have been used, but again you'd either need to custom cut conduit and add female conduit adapters to stick it all together, which rather adds to the parts list, or you could use a couple of bell mouth bushes to hold it all together. Anyway, this solution is 1 part instead of at least 3, although its internal rubber bungs all need to be removed and it only seems to come in red. The only other nuts and bolts item to mention is a rather large IP enclosure mounted on the rear. Like with my own Twat Cave test rig, this box contains some meters of wiring so that our dead tests don't add up to the low end of fuck all. This enclosure is sized at 240 by 190 by 90mm and is about as small as we can get away with here. It connects to the CU via a hole through the backboard, and for this I would recommend at least a 32mm hole. I'm using 2 20mm holes because Nick Bundy and I underestimated it and fucked things up back in October, but you don't want to know about Nick's ineptitude, so I won't mention it here. At least, not any more than I already have. Anyhow, hole size is not important so long as you can push your length through without scraping the sides too much, so to speak. So use 1 hole or more as per your own preference. But the point is that you need some wiring distance between your breaker and the accessory, otherwise you'll be measuring sod and indeed all. So all that wire has to be housed somewhere. For the ring circuit, which will consist of 2 single socket outlets in our rig here today, I've spooled off 8 meters of 2.5mm brown and blue wiring for the line and neutral, and 8 meters of 1.5mm green yellow for the circuit protective conductor, which I've taped together along their length. If this were a real conduit installation job, I'd use the same CSA across all cores, and if we went by European wiring regulations, we'd have a CPC that matched the line conductor. No ring circuit at all. Nonetheless, I am making this video for the UK, so to see something interesting, we'll go with a CPC that's 1.67 times smaller than the live wiring, so that the test data matches what would be seen if we were using 6242Y or twin and earth cabling, which tends to be the go-to on these grey and windswept shores. So despite these 2 socket outlets being physically adjacent to each other and to the CU, the wiring for them will actually be 8 meters long, looped, taped and contained in the IP box behind the board. When we come to undertake some ring end-to-end measurements later, we should see some appropriate numbers pop up. For now, the two ends of my ring wiring are brought out into the consumer unit and to the first socket accessory. For the radial socket outlet and the lighting circuit, I'm going to mix things up a bit, as I'll measure out 8 meters of brown 2.5mm for the socket, but also 8 meters of brown 1.5mm for the lighting, and I'm going to tape these closely together throughout their length. The neutral for each of these circuits will also be 8 meters at 2.5mm for the socket and 1.5mm for the lighting, while the CPC for both circuits will be 1.5mm throughout. Unlike the line wiring, the neutral and CPCs for both circuits will be run individually and will be looped separate to their respective brown line wiring for reasons that will become clear during testing. Once in place, all that wiring can now be sealed up in the IP box, as the ends have now been pulled through, ready for connection to both the CU and to the first accessory of each of our 3 circuits. The next step will be to wire out the remainder of each circuit and to attach the accessories themselves. For the ring sockets, that means adding a few centimetres of wire between the upper and lower socket and a return feed from the lower socket all the way back to the breaker. I'll also be adding 2 standard face plates. I'm mainly using Hager Solista accessories because they're easily available here and provide a robust and well-made solution for their money. I don't recommend going too cheap with store brand accessories, as they tend to have terminal screws made of cheese and probably won't take kindly to too much twiddling and fiddling over time. You know, it just occurred to me that had I built this rig with the backboard oriented in a landscape rotation, I'd have had a much easier job fitting the whole of the damn thing into the shot when it came to filming. What an asshole! For the radial socket circuit, I'll be sticking on a USB equipped outlet. This one is made by MK.
Okay.
And was chosen because it's cheap without being nasty. The additional 16 amp breaker I installed into the consumer unit, as I showed earlier, will serve this circuit. On the lighting, I'll be installing wiring to support 3-way switching with an intermediate switch in the centre. There's no advantage to a 3-way switching arrangement in terms of operation and testing, so you could just leave it as a single switch to save effort and expense. I've also pulled a CPC through so that one is present at all accessories. That's not needed here, although it is good practice. There's nothing to terminate it onto in the bottom apparatus, so I've stuck an orange Ideal splice line connector onto it to keep it out of trouble. The lamp holder itself needs to have terminals that support the loop in-out wiring method, and a couple of M4 bolts will be required to secure it to the angle box. One curveball here is I'll also be fitting a 1.2 ohm resistor between neutral and CPC at the lamp holder. Aside from the backboard, this resistor is the one other item we won't be able to obtain from the likes of CEF. An affiliate link from Amazon is in the description, although the likes of RS, Farnell and CPC can also supply such. Once the accessories are all in place, it's time to terminate the consumer unit. It's fairly obvious as to what's what. The ring wires are all together, while the 2 radial circuits each have different sized cores, which helps to tell them apart. The only thing you might need to buzz out is the CPC if you didn't mark which was which on the radials. I'm not aiming to be too neat here, it'll all end up being disconnected again when it comes to testing anyway. I appreciate that I'm covering the physical construction in a fairly brief form, but again, the assumption here is that you know how to bolt a basic ring and radial power circuit and a 3-way lighting arrangement together. So far, this is just a simplification of the kind of thing everyone builds in year 1 at a further education college when taking their first step onto the Sparky ladder, albeit with some meters of additional wiring added and a couple of specific construction points to show up something interesting when we come to testing. Coming off the consumer unit is a tail gland, through which I'm shoving 2 6181Y 10mm double insulated tails. Why 10mm tails when most installations you'll find in Blighty are 25mm? Well, again, it's because this is a test rig, and CEF sell 10mm 6181Y by the metre, so we can keep the costs down and make the engineering simpler. It's for that same reason I'm also running in a 10mm main earth instead of a 16. If you want to cut these to size, run them neatly, cleat them to the board, or whatever, you go right ahead. Do be sure to leave Barrett Singh loops, just like my own test rig, which I put in when Amy Barrett Singh came to visit me in 2021, where we played with a TIS MFT eco tester, and that's so we can attach a clamp meter, as you'll see later. If you do go with 16 or 25mm tails, you may have problems connecting them to the next part, which is a standard 2-pole isolator. I'll be using a ClickScoreMore 20 amp model with neon indicator. You'll get a 10mm into the terminals of this thing, 25mm you won't. You could use a different isolator, such as a rotary model, but I recommend something with a visual indicator to show when the thing is live. The tails and earthing enter another 47mm conduit apparatus, this time via an ordinary 32mm stuffing gland I previously drilled a hole for. Entering the side of the same accessory is a 16mm stuffing gland I've also fitted, which has a 2-core cable and a standard BS1363 13A plug top. These were just chopped off an old appliance, but a bit of 2-core cable and a plug are easy enough for anyone to source. Note that there's no CPC in the supply cable. We won't be connecting the test rig to the supply earthing system. Instead, line and neutral from the supply cable pass through the 2-pole isolator to get to the CU. However, neutral also connects to the main earth of our test rig thanks to a Sigma safety terminal, which is really just a fat connector block that can accommodate the 10mm wiring. Joining neutral and earth here simulates what's happening in a TNCS supply head, but it means when we come to piss around with RCD testing later, it won't take out anything upstream back on my actual home consumer unit. If you wanted, you could add a meter onto the tails or use a real service cutout as I've done on my own test rig, but these elements add to the cost, complexity and size without giving us any additional advantage we can make use of with our multifunction test instruments, so I've omitted them from the build here. So that covers construction. For better or worse, this thing exists. All that remains now is to put it through its paces, and I'll be using my Mega 1552, mainly because it's in calibration and it's dead straightforward to operate. Anyone equipped with a more modern MFT will have additional whistles and bells, although probably buried in menus somewhere. Nonetheless, we will see some other MFT action in this video. I'm going to fill out the all-new schedule of test results on EasyCert as I obtain my test data. I've spoken of EasyCert before and my complaints about this fucking form, so there's no need to delve too much into that here, except to say that this schedule and this software are each designed by people who really ought to try it out in the field themselves sometime. Anyway, the form we're now stuck with, thanks to Amendment 2's tomfoolery, and there's no point me swapping EasyCert for anything else, because all certification software has flaws, and I'd merely be exchanging one set of stupid for another. We can ignore the DB details fields for now, most of it doesn't apply anyway for a test rig, and we'll do live tests such as ZSDB and IPF later on. Circuits 1, 2 and 3 are our ring circuits, radial socket and lighting respectively. For type of wiring, we'll go with C and reference method B. It doesn't really matter here, it's the test data that I fired this fucking thing up for. Number of points can suck my balls, as I never provide data for that, as I droned on about in my previous EasyCert video from February 21. Sadly, Amendment 2 did nothing to address the fact that different people count points in different ways, which means the number I have in my head may be at odds to the one in yours. So while the IET can't or won't clarify the definition to address this long-standing issue, I won't be populating this field. I've already given wiring sizes, 2.5mm for line and neutral on the sockets with 1.5mm for CPC, and 1.5mm also for the live wiring of the lighting circuit. Maximum disconnection time is 0.4 seconds as I'm treating this test rig as a TNCS arrangement. Overcurrent devices are BSEN 60898 Type B at 32A, 16A and 6A respectively. Breaking capacity for all is 6 kA. EasyCert autofills the maximum permitted ZS, and I have that field based on 100% of the value given by BS7671 as given in table 41.3. You can set EasyCert to show the 80% value shown in table B6 of the on-site guide, but this field is asking for the maximum permitted, not the value with some leeway built in. If the measurement you take is above the 80% value and below the 100% value, then you need to make an engineering determination as to whether it's acceptable or not based on how you've designed and installed the circuit and what it's doing. Anyway, I don't want to blab on about that too much. Suffice to say that an NIC EIC assessor would expect to see the 100% value in here, and I know that from a webinar of theirs that I sat in on, so go argue with them if you want to argue with anybody. The RCD is a 61008 Type AC rather than a Type A in this case, which I find daft, because the writing has been on the wall for Type AC since 18th edition came out in 2018. so why this BG bollocks bought in late 2022 still has Type AC is bananas. Most manufacturers switched over to Type A long time ago, and even then it shouldn't have been that much of a surprise, as countries such as Germany dropped Type AC all the way back in the 1980s as far as I understand it, so the UK is unfashionably late to the party and pissed up on Blue Nun as usual. Anyway, this RCD is rated at 30 milliamps, 40 amps. The stupid Amendment 2 form is way too big to fit onto one screen these days because, again, those cocksuckers who designed it never tried using it on a laptop while sat on a plant room wanking chair or stuffed in an understairs cupboard. But if we scroll to the right, we can see the actual meat of the thing that we're interested in, the test result fields. Time at last to break out the gear and see some numbers appear on here. For the radial socket and lighting circuits, there's no end-to-end data to gather. However, for the ring sockets, we want to know that we have continuity from the end of the wire going out of the CU to the other coming back in. Before we get a definite digit onto the screen of my Mega, let's plop in a spot of arithmetic to see what that number ought to be. If I go and grab my on-site guide and open it up to table I1, we find it says that a wire with a CSA of 2.5mm will have a resistance of 7.41 milliohms per metre. And I know that during construction I spooled off 8 metres each for the line and neutral of my ring circuit, which, you'll recall, is all stuffed away right at my rear IP box. We can express 7.41 milliohms either as the exponent, i.e. 7.41 times 10 to the minus 3, which is how I was taught at college 30 plus years ago, or we can move the decimal point 3 places to the left to show it in ohms, as 0.00741 ohms per metre. Go with whichever works for you, the end result will be the same. 7.41 milliohms multiplied by 8 metres comes to 0.059 ohm. The MFTs I have here only show to 2 decimal places, so we can expect to see a figure of around 0.06 on the display, give or take a little. It's a very low number to be picking up, and the wire isn't continuous as it's been broken and terminated at each socket. Still, if the tester is calibrated, the leads are sound, and it's been nulled before we begin, there shouldn't be any real surprise. Ideally, I want all of my resistance tests today to be within 0.05 ohm of what's been calculated. If we measure line R1, we can indeed see that it's clocking in about where we expect it to be. Obviously, neutral RN should test the same as R1, as that too is a 2.5mm wire of the same length. And indeed, when we put the Mega on there, we get near enough the same magic number. For R2 it should be different, as although the length is the same, I ran that as a 1.5mm conductor, which is 1.67 times smaller, because 2.5 over 1.5 is 1.67. It should therefore have 1.67 times the resistance, so if we take the 0.059 ohms, which is the resistance we calculated for a 2.5mm conductor, and multiply it by 1.67, we get 0.098 ohms. Just to check that figure, if we again refer to table I1 and find the resistance stated there for a 1.5mm conductor, we can see it's given as 12.10 milliohms per metre. 12.10 milliohms times 8 metres equals 0.097 ohms, which we just worked out is 1.67 times higher than the figure for the 2.5mm wiring. So there you go. We're all wanking off the same porno page here. My Mega should therefore report back something around the 0.10 ohm mark for little r2. Let's undertake the measurement, and there you have it. Lovely stuff. It's always nice when the maths just works. And now that those test readings are in the bag, let's get them into my easy search schedule. Next we can perform the R1 plus R2 measurement by connecting each line to its opposing CPC. I'm going to keep the same probes on my Mega, but use a socket adapter to mate them with my socket fronts. Again, some small resistance may creep in through the mechanical connection of the probes with the adapter and the adapter with the sockets. On older sockets, a few replugs and some fingering of the switch can often afford you a better connection if things aren't reading quite right. We know R1 measured at 0.05 ohm and R2 is 0.09 ohm from our previous tests, so if we add those together we get 0.14 ohm. Split that over 4 conductors, as there are 2 line wires and 2 circuit protective conductors going from our MFT at the socket back to our cross connect at the CU, and we get 0.035 ohm. So we're looking for something close to 0.04 on the tester's display. A quick test at each socket confirms this reading closely enough. So that proves we haven't got line and neutral reversed, our connections are present, correct and tight, the socket switch operates correctly, and that our socket faces aren't exhibiting a high resistance due to wear, tear or foreign ingress. Sometimes you'll come across a complete bird's nest of a consumer unit where it's just too difficult to cleanly get the loop on line to opposing CPC, in which case you can leave them connected at the CU and instead stick the cross connect on at an accessible socket, allowing you to then test all other outlets. That's something one can try on this rig as I'm showing here. Both ring sockets are giving me 0.05 ohm as the R1 plus R2, so I'll plumb that into EasyCert. It's slightly above the 0.04 the arithmetic worked it out to be, but that's okay. Of course, I could have installed a spur arrangement onto my rig with a few more meters of wiring, which would have handed us a higher R1 plus R2 figure. Anyway, the R2 field is next, and that would usually only see an entry if something like a bonding path were being measured. On my test rig, if you want to measure R2, i.e. any circuit CPC from source to destination, then you go nuts and populate this field. By default, EasyCert sticks NA into it. I'm going to leave it as I've already verified continuity of the circuit protective conductor through the tests I've just undertaken. When ring testing on initial verification, we also loop line and neutral, so that's R1 to opposing RN, which I've always found a bit odd. Surely looping neutral to CPC would be better, as that should give the same results as R1 plus R2, which we've already measured, so it would be something of a checksum process and would serve to indicate there being no loose connection on the neutral side, which is especially relevant in this age of AFDDs that can trip off on a dicky neutral. Still, the IET know better. So when we connect line to neutral, what should we see here? Well, we know a 2.5mm wire has a resistance of 7.41 milliohms per metre. That's the CSA of both line and neutral, and we have 8 meters on each, making 0.059 ohms for line and the same for neutral. So the formula would be R1 plus Rn divided by 4, because, as before, there are 4 wire paths back to our cross connect from our test point. Therefore we get 0.059 plus 0.059 divided by 4 equals 0.0295 ohm, or near as damn it. A quick shuffle of the tester's probes to move it to neutral, and hopefully we're going to get the number we expect. Well, close enough. If you've built this thing and you're not getting the numbers you think you should, check you correctly measured the wire lengths, they're terminated properly, the tester's probes are nulled, the tester is giving out reliable data, use a cal card or a chat box if available, and that any adapter in use or the sockets themselves aren't shit and introducing additional resistance. You can eliminate adapters and socket fronts by using probes to test at the rear connection point of any accessory. Of course, there's nowhere on the schedule to record R1 plus Rn, but it's a part of initial verification nonetheless. Moving on to what this bastard form is next asking for, and we have insulation resistance test voltage, which varies depending on whether it's an initial verification or periodic inspection. Let's assume this ring circuit is a wholly new install, in which case BS 7671 table 64 requires us to test with our instrument set at 500 volts DC for this type of circuit. Therefore, that's the number we'll slap in here. I know I can safely test between line and neutral at 500 volts because all we have on this circuit are 2 standard socket outlets with nothing plugged into them. I only need to connect to one end of each wire, as I've already proven continuity from one end all the way through to the other. Performing the test gives me an off-scale high reading for this instrument, which is greater than 299 million ohms, or 299 mega ohms. Some people say it's megohm rather than mega, but mega is the term for a unit that's to the power of 10 to the 6, which is why we have megabytes, megajoules, megavolts, megatons, and so on. When was the last time you heard anybody talk about a computer file that was so many megabytes in size? Never, that's when. It just doesn't happen anywhere else, so bollocks to you if you insist it should be megohms. There's also no reason here why I can't IR test at 500 volts between live conductors and earth. So I'll reconnect the CPC conductors to the earth bar, attach the green probe of the tester to that bar, and then attach the live probe to both line and neutral simultaneously. Again, I only need to connect to one end of each. I could test line and neutral individually to earth if I wanted, but being in the habit of joining and testing them together is good practice, as if there is a load connected that I may have missed, then it shouldn't matter. To show that, I'll plug in a missed load, such as this computer. The 500 volts from the tester will be applied to both line and neutral at the same time, therefore there is no potential difference between them, and the sensitive electronics in the computer won't be damaged. This is the same as what a pat test does. It hits both line and neutral at the same time and with the same voltage to see if anything comes back down the earth conductor without killing the equipment under test. Switching to 500 volts, and when I run the test, it's again off scale high for this instrument at greater than 299 mega ohms, which is what I expected. Other testers may have a different scale for IR, many being 999 mega ohms at 500 volts, but it doesn't really matter. Anything that can read into tens of millions of ohms will be enough. After all, the pass point for this kind of circuit is just 1 mega ohm. As far as certification is concerned, I can pop in the live test result. That's the figure for line neutral, and the live earth test result. I can also tick the polarity box because if line and neutral had been reversed, my R1 plus R2 test wouldn't have worked out. And that ends the dead testing for the ring socket circuit. Moving on to the radial socket, and this is simpler because we're straight into plain old R1 plus R2 testing by placing a loop between the line and the earth bar. But before we run the test, let's figure out what number we should see. The 2.5mm line core we've already determined is 7.41 milliamps per meter, with 8 meters adding up to 0.059 ohm. The 1.5mm CPC core we've already determined is 12.10 milliamps per meter, with 8 meters adding up to 0.0968 ohms. Adding the line to CPC means we're adding 0.059 to 0.0968, which equals 0.156 ohms. Let's slap the tester on. And yeah, well, that's near enough for me. Remember, we may get some small losses through the connection points, the socket face and the adapter, but we're well within 0.05 ohm of where we want it to be, which was, well, the math said 0.16, so that's good enough for me, mate. This time, however, things are going to be a little different when it comes to insulation resistance, because unlike the last circuit, this one has a permanently connected USB socket, so we have a fixed load between line and neutral that we cannot isolate. If this were initial verification, then regulation 643.3.3 would require us to test the wiring at 500 volts before any sensitive accessories are connected. Of course we can do that here, but instead I'm going to treat it as though it's a periodic inspection of an existing circuit where it's either impractical to wire out all loads or where I can't be completely sure I've done so. In this respect, we can drop the tester to 250 volts DC and skip the line to neutral tests as a limitation. If this were a condition report, we'd state why this limitation has been applied, of course. If it's an electrical certificate for a new installation, then limitations are not permitted. If you put it in, you test it, mate. With this socket and its sensitive electronics still wired in circuit, I'm going to remove its neutral from the neutral bar, connect my IR tester to line and neutral together and test them both simultaneously to the earth bar. There we go. As stated previously, this means there should be no potential difference across line and neutral that might spike the electronics of the USB socket, and when I run the test at 250 volts, we get an off-scale high at over 99.9 mega ohm, a lower full-scale deflection than the 500 volt setting, but no matter, so long as we're over 1 mega ohm for this kind of circuit, then it's hand jobs for all. Again, the result gets whacked into wanky cert, and the polarity box can also be checked because had it been reversed, the R1 plus R2 wouldn't have worked out earlier. Although that wraps up the dead testing for the radial socket circuit, at least as far as the schedule of test results goes, I would recommend performing an Rn plus R2, which will act as a checksum for the R1 plus R2, as it should give the same number. If it's substantially higher, then that would act as an indication of a loose neutral, while lower would indicate there was an issue with a loose line and that the prior R1 plus R2 result may have been out. I tested this circuit at 250 volts because of the fixed load that's present, but what if I had applied a higher test voltage? Although I dropped the test to 250 volts, with no potential difference across line and neutral, I could ramp this fucker right up to 1000 volts without causing any headaches with the electronics in this socket. Look, I'm doing it right now. Still, 250 volts is best, as the IR test can otherwise be skewed by any surge arresters or filters which may be present in accessories that have been left in circuit. Stick in more than 250 volts and they'll kick in and suck your numbers down artificially. Although I've just pumped 1000 volts DC into this USB socket, we'll live test it later and I'll bet you it'll still work just fine. And that wraps up the dead testing for the radial socket circuit. Finally, I'm onto the lighting, and it's back to R1, R2 testing by looping a line once again to earth. Like the others, this is an 8 metre circuit, this time with R1 and R2 each using 1.5mm wiring, and if you'll remember from earlier, that clocks in at 12.10 milliohms per metre. 8 metres line plus 8 metres CPC equals 16 metres in total. 12.10 milliohms times 16 meters equals 0.1936 ohms. So connecting the tester here should give a rounded figure of that sort. We can test on the loop connector of the lamp holder, which is giving us a figure of 0.21, which is about what we expected. And we can also test on the switch side, where the result should remain about the same for each switch. We do each one in turn. It'll be a little higher going through the switches, of course, as there's additional wiring, connection points and the switch contacts themselves being brought into play, but that's all looking pretty good to me. I measured 0.21 ohm at the loop and 0.24 ohm through the switches, so it's the higher number I'll be putting into the paperwork. Moving on to insulation resistance, and this time we are going to see a fault thanks to the resistor I placed during construction between neutral and earth. I'll be testing at 500 volts as though it were initial verification, although we'll see this resistive fault regardless of what test voltage one were to choose. If I test line to earth with no lamp present, then we ought to get a high pass, as indeed we do. I'm just going to flick through all switches to ensure every core gets tested. Lovely stuff. By removing neutral and testing that to earth, what we should see now, of course, is an insulation resistance collapse to zero. Oh, there it is. And of course that's because of the resistive path in place in here, which we can pretend is something like water or some kind of foreign contaminant that's sitting between the terminals. We don't even need the IR tester in this instance to pick this up. It's only 1.2 ohms. So if I switch it over to resistance, well, there you go, we can see it there for ourselves. Although the live wiring passed the test with flying colours, live wiring to earth crashes and burns on the paperwork. Table 64 states the minimum IR for this circuit should be 1 megaohm, so a fault of this nature must be corrected before we proceed with any further testing or with going live. For now, I'll just disconnect one end of the resistor, as I'll want to introduce that fault later on to bulk up some of our live tests. Anyway, that's it for dead testing, so with the protective devices off, I'm going to plug in and we'll go live. Isolator on. Super duper. Lovely stuff. Okay, now that the consumer unit is juiced, I can get the ZS at dB or the impedance external to this board, the ZE. Simplistically speaking, for TNCS we expect that to be below 0.35 ohms, for TNS below 0.8 ohms, and for TT below 1667 ohms, although ideally below 200 ohms. Obviously the reading I'm going to get here today depends on the ZE of the property I'm physically at and the ZS of the circuit I've plugged the test rig into. Here I'm on a TNCS supply, plugged into my wall-mounted test rig circuit and running off an extension lead, so it'll be high, relatively speaking. On the Mega we can run this as a 2-lead test, even though there's an RCD on my supply upstream, and that's because you'll recall this contraption has neutral and earth joined at the incoming isolator, so any RCD socket circuit I'm hanging off won't see an imbalance. We can see the Mega is recording a voltage of 246 volts AC. To get the impedance, I'm going to disconnect the supply earth as I would do in the real world. That's to remove any parallel paths such as gas and water bonding services. Not that any are present on this rig, but it's best to adopt the correct practice. I'm going to switch over to the Mega High Loop 2-lead test function, which will start automatically once it detects a voltage. There she goes. And in my case here today, the ZS at dB clocks in at 0.62 ohms. Now that we have measurements for voltage and impedance, we can get an idea of what our fault current would be. That is, the current that would flow if I rather foolishly connected line directly to earth or neutral here at the CU. A smidgen of Ohm's law tells us that I equals V over R, so 246 volts divided by 0.62 ohm would be 396.77 amps, or 0.39 kiloamps, as fault current is usually expressed in thousands of amps. I'll reconnect the supply earth so that I can take a prospective fault current reading between the earth bar with any parallel paths connected and the incoming line. And if I switch the Mega to High Loop PFC, we'll see if we measure something near enough what has just been calculated. Again, it does the test automatically, this particular instrument, and we get 0.37 kiloamps, so that's good enough for me. Now I'll take the prospective short circuit current between line and neutral, which here ought to be exactly the same, at least on this thing. That won't be surprising in this case, where the tails and earthing all have the same CSA and it's mimicking a TNCS arrangement, but in real situations it may read otherwise, where the CSA of the tails are bigger than the earthing and the supply type is different. It's the higher of the two readings one would record on the schedule. Speaking of which, while I'm on this frigging thing, we can also place our external impedance figure I measured earlier. Now that we know the external impedance, we can add that to the R1 plus R2 values of our circuits to show a calculated ZS figure. This is permitted by 643.7.3.1, which says the impedances shall be measured or determined by an alternative method. Well, calculation is a perfectly valid alternative method. Our calculated ZS numbers are therefore 0.67 for the ring, 0.80 for the radial socket, and 0.86 for the lighting. I'm being a bit naughty here because I'm ignoring the IR fault of the resistor, at least as far as the paperwork goes, which is why PSCC has highlighted it in red. At the moment, the fault resistor isn't in circuit, but it'll be back later, so we'll ignore that for now. I can check my calculations by performing some measurements. Let's go back to the two ringed socket outlets that are now energized. I'll connect the Mega on the no trip loop setting. There we go. And that's because, of course, we're going through the local RCD here. Each of these sockets should show the same measured figure when we put the tester on there, and maths being maths, it should add up to what we just plumbed into our schedule after adding our ZE to the R1, R2, i.e. around 0.67 ohms. Prepare to be stunned. Oh yeah, that's rather more than I figured. Let's try it on Nigel's 17 series. Lorks a lordy, that's even worse. That's a good half an ohm out from where we expected it to be. What gives? Well, this is a fairly rare example of RCD uplift that I've managed to catch in the act. I say rare, I've only come across it a couple of times out in the wild, so for it to exhibit itself here is rather fortuitous, at least as far as making this video goes. What's happening is that the Mega instruments are misreporting the impedance as measured. That extra half an ohm is not part of the earth fault loop impedance. Instead, it's an unwanted function of the Mega's 3-lead non-trip test procedure. If you don't believe me, here's the Metrol MI3125 performing the same test, yet returning something closer to the calculated result we expected to see. It's the same with the Metrol MI3100S. And here's the Ethos 8400 also reporting in closer to the mark. It's not unusual for the no-trip test to introduce a bit of overhead to the reading, but half an ohm can make the difference between a pass or fail when testing a circuit. I'm surprised the Megas are getting it wrong, but Nick Bundy and I saw exactly the same results with his 17 series Mega back in October, so it may be an issue with these older Mega models, or that a firmware update is required. I don't know, if this happens to you out in the world, go with the calculated data obtained via a low ohm test for R1 plus R2 and a 2-lead test for ZS at dB, as those figures are more accurate. just to show that this is down to the RCD, if I bypass it with a couple of wires as a jerry-rigged frig and switch the megas back to their 2-wire testing, they now each return with an accurate result. Despite up to half an ohm appearing on the live tests, if we measure the resistance through each side of the RCD, with the power off of course, well, that overhead is nowhere to be seen, which rather proves we're seeing an unwanted product of the test itself rather than a valid component of the earth fault loop path. As it turns out, I can also switch out this BG RCD for another one I have to hand. This is exactly the same model, except it's rated at 80 amps instead of 40. With the replacement RCD, the Mega No Trip works just fine, so it's definitely a characteristic of how this particular RCD behaves under Mega's 3-lead test. As I say, we're rather lucky to have caught that. I've been keeping an eye out for an RCD uplift event for some time now without success, so it's great to have it on the test rig here where I can reproduce it at leisure. Anyway, my other instruments largely confirmed my ZS calculations, so I can leave them be or plop in the slightly higher no trip numbers the likes of the Metrol testers were showing. For the sake of brevity, I'm not going to go to too much effort over ZS readings for the socket radial or lighting, at least not on camera. You may take my word for it that with this RCD, the numbers clock in about where expected, and with this RCD, they're up to half an ohm out, at least with these two test instruments. On to RCD testing and a change introduced in 18th edition Amendment 2. Regulation 411.5.3 requires an RCD installed for fault protection to trip before touch voltage exceeds 50 volts. So a 30 mA RCD could be on an earth rod as high as 1667 ohms because 1667 times 30 milliamps equals 50 volts. That RCD would be tested at 1 times operation on a certificate or report to verify correct functionality. When it comes to RCDs for additional protection, Regulation 643.8 previously asked for timing data based on 5 times the device rating, with a trip time to be no more than 40 milliseconds. This all went a bit to cock as some newer RCDs didn't play ball with the 5 times test on some models of test instrument. So in Amendment 2, 643.8 was revised, and now all RCDs, whether for fault or additional protection, are tested at 1 times operation, with a reaction time expected within 300 milliseconds for a non-delayed device to BSEN 61008. Uplift won't cause us any other headaches, so I've reinstalled my original 40 amp additional protection RCD in preparation for obtaining this timing data. Although our schedule only requires the figure for 1 times testing of type AC, one can of course perform all sorts of tests, including half times, 5 times, type specific and ramp testing until the cows come home. Again, the linked neutral and earth at my incoming isolator means it'll be the RCD in the rig that pops and not anything upstream. I'm testing at the radial outlet, which is as good as any. I only need the timing from 1 circuit, no neutral connections needed, and my 1 times figure at 0 degrees is 8.2 milliseconds. Let's switch that to 180 degrees, and we get this time 19.7 milliseconds, so it's that higher timing that I'll be piping into the schedule. For shits and giggles, I'll also ramp test this bastard. With a 30 mA rating, it should pass a 15 mA half times test, but trip no higher than 30 mA as an absolute maximum, as the rating of an RCD is its highest cutoff. A ramp test here clocks this particular unit at 27 milliamps, which is within the window we want to see. If we'd have left our resistive fault in circuit at the light, then that would have banjaxed our timing, because some of the test current would escape to earth and bypass the RCD, making it take longer to operate. So far my test rig has performed the basic operations needed to gather data for the schedule of test results, but there are still a couple of things this rig can demonstrate for us outside of what BS7671 asks for. I'm going to reconnect the resistor between neutral and earth on the lighting to reintroduce the IR fault we saw earlier when dead testing, and that will allow me to tickle the bollocks of earth leakage. With the resistor back in place in here, any lamp I place into the holder will draw a current from line across its load and down through neutral, but some of that current will leak across the resistor to earth. An LED lamp of just a few watts ought to work just fine, while a higher wattage lamp such as this 60 watt incandescent will draw more current and therefore a larger earth leakage, which may trip the RCD. Let's see what happens with this 35 watt incandescent lamp. Interesting, but if I reset this quickly enough times, the filament you can see is trying to light each time, and there we go. Every time it lights up, it has a chance to warm up a little bit, which increases its resistance, and eventually the inrush current is reduced by just enough to break the leakage down below the threshold of the RCD, allowing it to finally hold its illumination. We can measure this earth leakage by placing a sensitive clamp meter, such as this rather marvellous TIS 570 model, around line and neutral on the Barrett Sing loops. If there's no leakage, then the current up line will balance that down neutral, and the net difference we read back on the clamp will be zero. However, if some current is dribbling away to earth, then this clamp meter will detect the imbalance. If I turn this on here, we can see the 12 watt LED lamp is working, but with a leakage current of 2.7 milliamps. That's well below the 27 milliamp trip threshold I measured for this RCD in the ramp test, so it isn't going to trip jack shit anytime soon. Let's put in the 35 watt incandescent lamp, and that's also working, but it takes our leakage 8.6 milliamps into our 27 milliamp margin for error. So long as the resistor is left in place, this lighting circuit will always be sensitive to what lamp may be employed, but there is a further twist. As this is an RCD rather than an RCDO arrangement, the neutral bar is common to all circuits. So our resistor being between neutral and earth on the lighting also effectively places it between neutral and earth for everything else. This means anything we connect to this consumer unit will leak current, regardless of what the lighting is doing. Allow me to demonstrate. I'm going to switch off the light circuit completely and remove the lamp. The fault may be physically at the lighting point, but because that places resistance common across all circuits, the lighting doesn't need to be energized or even have a lamp in place for the fault to manifest itself. Instead, I shall plug in this fan heater into any of our 3 sockets. Doesn't make any difference. And on the 20 watt fan only setting, we get, well, about half a milliamp of leakage current picked up by the meter. When I switch on the 1 kilowatt element, that jumps to nearly 14 milliamps of leakage current, and switching it to 2 kilowatts, well, there goes our RCD. So that bumps us over the trip threshold. Let me introduce a second appliance in the form of a hairdryer. The nice thing about this thing is that I can ramp it up through different speed and heat settings, and we can watch the leakage increase as that happens. While I do manage to edge the RCD up close to its ramp point toward the end there, when I tried to go any further then it dutifully tripped off. The interesting thing about this fault is that the client will report it happened only when they were using the hairdryer, so they think the fault is down to that. The electrician they call in might discount the hairdryer itself. After all, it's class 2, so unlikely to cause an RCD trip in of itself, as it has no earth for current to leak down. Nonetheless, if said spark doesn't know their toffee, then they may conclude the fault as being on the socket ring circuit, as that was the only circuit serving current using equipment when the RCD clocked off. It's even repeatable. Put the RCD back on, turn the hairdryer up to the max, and off it pops again. That's got to be a fault on the socket circuit, right? It can't be lighting. That's not even switched on at the board. Well, that's why you never take a customer's word for it, and you always IR test all circuits downstream of an RCD at the start of a trip job and before anyone mucks around with the place. To avoid any wild goose chases, you want to see which circuit has a low number, and we know from our earlier testing that here, it's the lighting. A neutral earth fault on any circuit will affect all circuits on a non-RCBO board, and this little arrangement here allows you to play with all sorts of loads to see leakage current and RCD tripping in action. But hang on, our 35 watt incandescent lamp is leaking nearly 9 milliamps, which is 3/4 of the way into our leakage budget before the RCD trips. So how come I can run a 1000 watt load off the sockets with less than 14 milliamps leaking out? Well, the effect of the resistor will be greater on whichever circuit it's placed on. If I remove it from the light and put it directly between the neutral and earth bars at the CU, well, if we switch on the 35 watt lamp now, we can see it's taking 0.7 milliamps on the lighting circuit. But if I were to screw that into a lamp holder with a plug top and plug it into either of our socket circuits, we get exactly the same reading again, 0.7, 0.7. If I move the resistor to the back of the radial socket circuit and plug the 35 watt lamp in here, we get 6.6 milliamps of leakage current. Yet the same lamp on the lighting circuit now gives us, wait for it, less than 1 milliamp, 0.6. So a localised neutral earth fault will have an effect on all circuits, but the effect will be greater on the circuit with the direct problem. All this prattling about shows that unrelated loads such as the fan heater and hairdryer can take out the RCD, but then so can a humble light bulb if it's physically closer to the fault. All jolly interesting, I'm sure you'll agree. Or not. I should also state that a 1.2 ohm resistor seems to be doing the business for me, but you may want to play with different values depending on what loads you have to hand and what effects you want to see. Just make sure that it's always placed between neutral and earth, because if you stick it onto line, this is what it'll do. Yeah, don't try that at home, folks. Anyhow, now that we've quite finished pissing around with the resistor, I'll leave that disconnected to bring all circuits back into reliable service. I earlier used an earth leakage clamp meter around line and neutral tails to measure some fault current, but if I move it to be around line only, I can now measure load current. Again, if we shove in a bit of Ohm's law, we know that my 1 kilowatt fan heater on a 240 volt supply should draw over 4 amps, as indeed it does. When set to 2 kilowatts, we should see about 8.5 amps. And there it is. There's one more feature of my rig that we can play with, and that's the effect of capacitance. You'll perhaps recall that during construction I ran the line wire of the lighting circuit separate to its respective neutral and CPC, and I tied it to the line wire of the radial socket circuit. This effectively makes an 8 metre long capacitor, 2 conductive parts separated by an insulator. In this case that's 2 lengths of copper wire separated by PVC insulation and a varying air gap along their length. When the radial socket circuit is on, regardless of whether it's pulling any current, an electric field surrounds its line wire. This permeates into the adjoining wire of the lighting circuit, causing a voltage to be induced and a tiny current to flow. While this won't trouble the likes of incandescent or fluorescent lamps, it can be just enough to actuate the electronics in a sensitive LED model. You'll need a bit of trial and error to catch it in the act, but I know that this 2011 GE lamp is susceptible to it. I'm going to place it into an E14 to B22D converter, and if I plop it into the lamp holder, we can see it operates as expected when the light circuit is powered. However, if I switch the light circuit off at the MCB, you will hopefully observe that there's still some light continuing to be emitted. We can consider this as a nuisance glow because if you turn the light off, you expect it to wholly extinguish. Just to prove that this ghostly glow is coming from the adjacent radial circuit, if I turn off the breaker for that, you'll see the light now disappears. With a very sensitive clamp meter such as the TIS 560, which has a 2 milliamp range, we may just be able to record the current, which is in the order of a few microamps. Gee up, this one's going on a bit, isn't it? Okay, if I take my Mega and disconnect the line wiring of the lighting circuit, I'm going to stick my Mega onto that floating line wire and put the opposing probe onto neutral. And then I'm going to switch that to volts. And what I'm going to do is I'm going to switch on the radial socket circuit, where you will observe 7 volts has been inducted onto the lighting wiring from that neighbouring circuit. The MFT is a low impedance voltmeter. That's so it can give you a voltage reading that won't make you shit your pants. I can demonstrate what I mean by that by using the TIS E217 multimeter. The E217 has a low impedance voltage function which, when set here, reads similar to the Mega at, well, 8 volts. However, if I switch it to the normal AC volt function, as most general multimeters would have, the reading jumps to 131 volts. You'll also notice the lamp is now aglow, whereas it wasn't a moment ago when I was on the low impedance setting. On that setting, the current runs through the meter rather than the lamp, as it offers, well, a lower impedance. On the higher impedance range, the current flows through the lamp rather than the meter, causing it to glow. So what's the actual voltage here, 8 volts or 131 volts? Well, it's an induced voltage, so its value varies depending on the impedance of whatever instrument you're trying to measure it with. MFTs are low impedance meters just so they can squash an induced phantom voltage. Otherwise, if I connected my Mega to the wire of this dead circuit and observed 131 volts, I'd poo my pyjamas and would be gingerly trying to find out what on earth was causing it. The Mega showing just 7 volts tells me it's an induced voltage with no real current behind it. I can safely touch this wire and the impedance of my body has an effect on the brightness of the lamp, but there's no danger, even though a standard multimeter may be measuring a voltage in 3 figures. I have 2 previous videos discussing LED lamps glowing when they shouldn't, and it's not always down to capacitance, but here it very much is, and that's down to the deliberate design. Had I run these 2 line wires separate from each other and with their respective neutral and CPC cores, then the electric field would have been dampened and the phenomenon wouldn't show up at all. I should state that finding a lamp that will play ball here may be tricky. This GE model is the only example I found among all my various weird and wonderful LED lamps that successfully and consistently demonstrates the phenomena. But even if you can't find a lamp that will give you a glow, you can still measure the induced voltage as shown to see how the socket circuit is affecting the lighting. For it to work on the rig, the radial socket circuit must be on, the lighting circuit must be off, but one of the light switches must be on. This is not how you would experience the problem in real life, because there the lighting circuit would be on but the switch would be off. The reason for the difference is that on the rig, the capacitance has been introduced on the 8-meter feed wire for the circuit, but out in the wild it would happen on a switch drop where there's one long energised core with an electric field and one long non-energised core, at least when the switch is off, which the electric field is permeating and inducing a voltage onto. The presence of a working circuit protective conductor between these cores would dampen the field, so you'll see this occur on unearthed lighting circuits or those whose CPC to the switch drop is not properly connected, wiring running singles, that sort of thing. The fix would be to rewire the switch drop with a working CPC and or to replace the lamps with another model that doesn't suffer from the issue. Replacing this LED spot lamp for this LED spot lamp puts paid to the problem here, simply because the electronics in the second lamp, well, they're just not as sensitive. Of course it works the other way round too, and energising the lighting will put a rogue 7 to 8 volts on the de-energised socket circuit, which you can measure from the socket face so long as the USB electronics in your chosen outlet don't squash it. You know what, speaking of that, I never did check to see if that 1000 volt IR test I did from earlier cooked the electronics in this thing. Well, there you go, that looks like it's working alright, doesn't it? Jolly good. Well, there you have it, no problems there. I'm wrapping this one up here. It's been a hell of a long day, but this is Test Rig version 101. Yeah, I'm going to leave that door open to any future new and improved versions, but this will allow anyone to have a practice with most of the features and functions of their own test equipment, remembering of course that you should only undertake building and operating such a thing if you consider yourself confident and competent enough to do so. Use it at your own risk, folks. Even if you don't build one, if you've patiently sat through this video, then hopefully you've followed what's been done and why. Oh, look at us, back in our windswept coffee hole.
Yeah.
A bit cold for it, isn't it?
It's a little chilly this morning. It's not icy though, so it's not too bad. It's not too
Mind you, if you're going to have a good Andrew Curl cigar...
Oh yeah, that's a big fat one, isn't it?
That's going to kill me before the end of this session.
Yeah, you'll be flat out on the floor before you've done that one.
Thanks once again, Andy, for smuggling these up your ass into the country. Bit noisy in our coffee hole today because there seems to be building work going on over there.
Yeah, yeah.
Well, you can't see. I know you're probably missing our specialist studios that we keep building. We spent a lot of time and money building a Lapland studio, didn't we?
Yes,
In Lapland.
yes.
We had a Father Christmas there, elves,
Oh, it was magical.
that fat fairy.
Yeah,
I liked her.
Yeah. Hey, that one with the funny wrist, like you.
Anyway, this video was supposed to go out sort of by Christmas, and it's kind of delayed.
Yeah.
So we didn't really. It's very expensive to pay these people, and because it's going to be Christmas is going to be done by the time the video goes out, we kind of just ran away and left them to it. So they're there right now, angry as fuck, I imagine, because we've kind of left them in the studio and
Nothing
we
like an
came out
angry
here.
elf. Nothing like an angry elf.
But that fucking fairy, I reckon she could do some damage with one of those candy canes.
Oh, yeah.
So yes, apologies for the lack of specialist studioage for this one, but this will be a long video because this will be the test rig video, which yeah, it's already delayed. It's already far more complicated than expected. We've already filmed it twice, once with you and once with Nick.
Yeah.
And that didn't work. So yes, forgive us for abandoning the coffee studio for something a bit simpler.
Yeah.
Anyway, some shout outs to do. First one is a whore. Nigel, would you like to read the first one there?
Ollie enjoys boys. Oh, I read that one wrong. Enjoy boys and have a good fun time on him.
I think he means a good fun time with some coffee as opposed to anything more perverse. The next one, please, Nigel. I'm too busy smoking my massive fucking cigar.
Yes, Andy Karush. Cheers, lad. Enjoyed the last video.
Well, goodness knows what the last video was by the time this fucking goes out.
Yeah,
It's so delayed.
They all seem to come out randomly.
Next is TestGear Junkie, who are Sammi and Ria, who are actually responsible for the test rig video and all the chaos that it brought. They actually came to see me, as I may have mentioned previously, and they say, pity that they didn't meet you. I imagine they dodged a bullet by not meeting you. Their mistake was to turn up at about 4 o'clock in the afternoon.
Yeah, I'm not there at 4.
Yeah. Nigel does half a day.
Got to be something going wrong if I'm still there at 4. DTS Electrics.
They've all been whores so far, haven't
Yeah, they have. DTS Electrics. When are we going to see a video of you and Nige with Nicey Boys Artisan Electrics?
I imagine when hell freezes over.
Yeah, possibly.
That's not because we wouldn't, but I'm sure they wouldn't.
Yeah, what would they want to be seen with us?
It'd be like
the likes of us.
pairing, I don't know, angels with demons, wouldn't it?
Yes, yes.
We turn up with our booze breath and big
Cigars.
cigar and our particular ways
Yes.
and phrases. Yes, no, I don't think that's they'll want us anywhere near their cleaner, greener output.
Yeah. And we've got Ross Llewellyn.
A virgin.
A virgin, yes. Love the videos, always informative, a laugh and a bit of bollocks. Okay. Enjoy the coffee from one Sparky to a right pair of tossers. Well, he knows us, doesn't he?
Thanks
He's
for
got us
noticing.
down. Yeah. What can I say?
Yes, thank you, Ross, and welcome to the club.
Yes.
Mr. Humbug, of course, who is very
course,
much not a virgin, and as usual doesn't have much to say.
No. John C10 UK.
That's the one.
Merry Christmas and hope to see more videos in 2023.
Yes, a belated Merry Christmas to all, and again,
yes.
sorry that this video didn't get out over Christmas as it was supposed to do.
Yeah. Well done, Nigel, on passing your motorbike test. Well, I've been riding bikes since I was a kid, so it was easy. It was just getting on the road that took me 40 years to do. So, thank you very much.
Another virgin.
Yeah.
Martin and Viv at BJ Rental.
I wonder what they rent out.
I don't know, but I could do with some of that. Please use the money for a repair kit for your inflatable Nigel, which did get some abuse over Christmas. As you may have seen in our Christmas musical video
Yes.
we bravely put out. It did indeed get a pounding over the Winter Consumer Fest. So thank you, Martin and Viv. And again, welcome to the state of affairs that is this catastrophic channel.
Didn't I already read Andy Karush?
We're so delayed that we've even got the same name read twice. Yes, Andy Karush,
right.
A second contribution. Again, I'm terribly sorry. Even this video won't have caught up with the coffee contributions. We are
Yes.
so behind with everything.
Yes, we've got to catch up this year. There's a resolution that probably won't be kept. We've got to catch up.
Maybe a couple of quicker, easier videos to make to catch up a bit. But, yes, apparently Andy's lovely Liz He wants to see Nige on his throbbing
twin, my lovely Bonneville. Yes, he says that rear view put her off a Pinot Noir.
Yeah, I think that was the green box video. Your ass hanging in front of the camera all the time.
Yes. Yeah. Well, you have to work in the positions you have to work in. Yes, my Bonneville doesn't come to work very often because my little Honda does about 150 odd to the gallon. Not that the Bonneville's that thirsty, but
why buy one motorbike when you can buy two?
Well, the Bonnevilles, I take the wife on the Bonneville, and we can go off places on that. You're not going to go on a motorway.
Don't get him started on motorbikes, for God's sake.
I'll leave it at that.
Jesus Christ. Jesus Christ isn't a contributor.
I was just going to say, is he next? GR Electrical RH17.
Another well-known whore to us.
And he's looking forward to us churning out more shite in 2023.
Yeah, let's see what happens, eh?
That's exactly what we'll churn out for you.
And the final coffee shout-outer for this session, and again, sorry, I know we're behind, and if you've contributed after the date that's been posted on the screen, then they will come. They will come.
They will.
It's just
no one left behind. And we've got Steve Skillern, still my favourite YouTubers.
He really ought to look around a bit more on YouTube, shouldn't he? There's a lot more out there, Steve.
If we're your favourite YouTubers, that must be some kind of weird fetish. That's all I
hope the audio comes out all right here with all this wind and the rattly stuff.
Yeah, it is windy.
Super Wanks. We have anonymous Mark Eastwood who has made a generous contribution. He's an orange Super Wanker.
Yeah.
Another white knuckle ride, he says. Tony Dunlop is a yellow Super Wanker, and he says that his contribution goes towards you having your own plate of cheesy chips, because I believe in the green box video I had one and you didn't.
I'm trying to lose some more weight because my knees are just dying. Eventually I'll be skeletal and my knees will still be done, and that'll be me.
You know, I've put on about 2.5 kilograms of Carlsberg recently. I'm now up to 75 on the scales. It's getting a bit bad. I need to do something about that. A special announcements. We had our inaugural Unreal Tournament 2004 session last week.
I had a great laugh. I had a whiskey, pizza.
You know what's annoying? The fact that as soon as we mentioned we were doing UT 2004 in whichever video it was been the green box video, Epic pulled the plug on the game.
An epic fail.
They've
18 completely
years,
got rid of the game.
They pulled it, but pretty much the same day we announced we were going to play it. So if that's not influencing, I just don't know what is. So you can't buy it in Steam anymore. So the only people who can join are either those who've already got it or those who can get it.
Yeah, there'll be ways to get it.
There are ways and means, we think.
There are ways and means.
But we want to say thank you to Rizzler, JS Cobb, LibC and WDWD.
Yes, thanks for shooting me many times, especially LibC and Rizzler. Thanks for killing me over and over again.
So they turned up as a fancy foursome and joined us as a even fancier twosome to make a sixsome.
Yes.
Which, you know, that's not a bad number for an 18-year-old game.
6 of us and a few bots.
I got hopelessly drunk while playing it, so my ability to play the game declined as the session went on. We'll have to post a new date for the next one.
Yeah.
If you go to dcess.uk, type UT 2004 into the search field, you'll get a web page that gives all the information.
Yeah.
This is fucking smooth, I've got to say, compared to my Asda cigars I normally buy. That's fucking nice.
Yeah.
So thank you, Andy, for sticking your big length in my gob.
Yes.
Your big smooth length. Nice aftertaste. You can put that on your CV. Anyway, we're going to wrap this up now because this video is hopelessly long, hopelessly late, probably hopelessly boring and inaccurate and shite as well, so fuck knows who's going to watch it. But we will catch up with the coffee shoutouts. More to come in 2023, hopefully.
Yep.
See you back in the proper studio maybe next time, maybe.
Maybe.
If the elves and Santa haven't trashed it in our absence.
Yeah, if we can get rid of them, we can move it off somewhere else, maybe. I don't know.
Yeah.
We'll figure something.
Yes. Happy New Year, if it is the New Year.
Yes, Happy New Year.
By the time this comes out. So long, suckers!
See ya.